Hello everyone, welcome back to my video series on doing web programming in OpenGL, WebGL. If you watched my last video, first of all, congratulations. The thing was like 45 minutes long just to draw a simple triangle. I did go meticulously over all of the basics, that's why it had to take too long. This one is not going to be as long. There's not nearly as much overhead material. We can just get straight to making the cool stuff. So in this one I'm going to introduce 3D programming. So we're going to make a spinning cube that's fully in perspective. So this is the code that we had last time, or at least the result of last time. This is what we're going to have by the end of today. And you have all of the tools, technically speaking, to do it with this if you wanted to be insane and do all the mathematics yourself. Because still I am just drawing to the same coordinates, you know, starting at 0 down here, or -1 to 1, -1 to 1, and all that. The difference is I'm going to be introducing a lot of math to do it for me. So this cube is defined as a 2 by 2 by 2 cube that then I have a whole bunch of stuff set up to transform that 2 by 2 by 2, do all the rotations, set up a virtual camera in a position in the 3D world, and then also map all those points into the two-dimensional screen space that we're going to be drawing. So I'm not going to cover the mathematics behind it that heavily. I'm just going to kind of show you what there is. So points are represented as vectors in 3D space, and there is a fourth component for those of you who have some familiarity with linear algebra or regular algebra, whatever you've seen vectors in. So say that cube was 2 units to the right, 4 up, and 5 forward from the middle of our world. We would represent that as 4 numbers together in a vector: 2, 4, 5, 1. The fourth component is always 1 for positions and 0 for directions. And I'm not going to get into why that is. And then there's matrices. A matrix is a 4 by 4 set of numbers that, in graphics programming, it represents some mutation or transformation, to use the linear algebra E word, to perform on a vector. So this one right here is the identity matrix, and when you multiply these two things together, you get this same vector out of it. A vector times a matrix is a vector, and a matrix times a matrix is a matrix. The basic ones are translation. You can have a translation matrix that moves an object in space like that, a rotation matrix that spins one around, and a scale matrix. I'm not going to go over how these are made, because we're actually going to be using an external math library in order to do all of that. Then there's also the view transform, which is a little bit more elaborate than those basic ones, and it creates, you can think of as an imaginary camera. So as an example, if we had a camera at space 1, 2, 3, and the center of the triangle was at 1, 2, 5, then you can apply the view transform matrix to the center of the triangle vector, and you would get the vector 0, 0, 2, saying how far away they are. 1 minus 1, 2 minus 2, 5 minus 3. Whoops, typo. And that's more or less true. There's also considerations taken for the rotation and which way is up of the camera, things like that. And then finally there's the projection matrix, which takes the 3D virtual space, wherever it is in the camera space of an object, and it applies that into the 2D screen space that we talked about when making this triangle, from -1 to 1, -1 to 1 on the x and y axes. And once you have applied all of those transformations to an object, you will get something like this. Cool. So the first thing is I am going to download this GL matrix. This is just a set of tools. You can see the source code even if you go to the GitHub page, which I'm not going to. The documentation is really all that's important. My internet may have just actually crapped out. No, it didn't. Phew, good. But this provides us the tools, and the ones that I'm most interested in is there's a map4.rotate function, which then gives you a rotation matrix, so something that transforms a point and rotates it around a different point. And then there is this perspective function, which is going to be really important. This is what does that projection matrix for us. It transforms from 3D space into the 2D screen space, and then there is a look at function that I want to use, and this is something that will form a matrix if we give it information about a virtual camera. We give it I, which is the position of the camera, center, which is where the camera is looking at, and up, which is which direction is up for the camera. Great. So in order to get this, it's just glmatrix.net. I'll put a link in the description. And you can come here to download zip file. Now, for those, I'm not going to do a tutorial on configuration management or anything like that, but if you use Bower and npm, this is a Bower package that you can use. So you would say Bower install GL matrix. Alright, I already have this one downloaded. I'm going to re-download it. And we're only interested in one of the files. It'll be under this folder. There'll be a folder called dist. That stands for distribution. You could, strictly speaking, go into the source too, I believe, but we're not going to. And then you have GL matrix and GL matrix min. They both do the same thing. As you can see, this one is much smaller. The difference is there's less white space, and they've changed variable names to be shorter in GL matrix min. I'm just going to take GL matrix in case we actually have to go into the source code. I don't imagine we will. I'm going to copy that. I'm on Windows 10, so I can directly copy from inside a compressed folder. You might have to uncompress it depending on which operating system you're using. I'm going to go, I had it under here, and I'm just going to copy that file right there. Great, so this is in the same directory as our last one, which is this. Then I'm going to pull up that project. Whoops, it was this one. And I'm going to also include that source code. Script source equals, oh phooey, what was it? gl-matrix.js. Script. Alright, now if I go back to this, and I look at the source, we should now also have that one included. Perfect. And so that gives us a whole bunch of functions, like mat4.identity. I'll just show off that. Now the way this one works is you want to make a float 32 array for all the variables, so identity equals new float 32 array with 16 elements, because that's how big a matrix is. Right now it's just going to be straight zeros, but if we say mat4.identity, and then we give it the name of that variable we just made, it then pops out and has been changed into the identity matrix. Now, it won't be represented as you do it in 4x4, but you can see the first row is 1000, then 0100, 0010, 0001. So that's the end of the math, I promise, that I'm going to do in this tutorial. You just need to know the concepts that matrices can do transformations like that. You don't need to know the how of it. That is beyond the scope of what I want to cover. Great, cool. So the first thing we are going to do is let's get that triangle spinning first. The triangle that we have already, because we're going to have to make a whole bunch of new points. I'm actually going to be covering two things. I'm going to be covering the 3D transformations, and I'm also going to be covering using index arrays to draw more complicated geometry like that cube. So, in our vertex shader, in the last tutorial, it was super boring. All we were doing is we were setting information and sending it straight to the fragment shader. The vertex shader did absolutely nothing cool on its own. It just said the position is equal to the position and the color is equal to the color. So in here, we're going to be changing it, and we're going to be applying those matrices. Now, the matrices do not change per vertex, so they're not attributes, but they're still inputs. They stay the same for all vertices, but they're still inputs, and the way we do that is through what's called a uniform. So I'm going to add a couple of those down here. I'm going to say uniform is a global variable. The type is going to be mat4 for a 4x4 matrix, and we're going to have two. The first one, well actually I guess we're going to have three. We're going to have the world matrix, the view matrix, and the projection matrix. So there's the world matrix, uniform, mat4, and view matrix, uniform, mat4, and view projection matrix. Great. So one thing is when you multiply two matrices together, you get another matrix that is what happens if you apply both of those operations. And the ordering is important. Depending on row major or column major, either the matrix that is multiplied before happens first or the one that happens after. In OpenGL, the transformations happen in reverse order as they're written out. So if I were to have, let's see, so the world matrix needs to happen first, and then the view matrix, and then the projection matrix. So this is what we're going to want, I'm going to bring this back down to one screen. We don't need index.html. That's the only change we made. Oh, let's do this too. Let's change the title. Rotating cube. Great. So in this line right here, this is an example of multiplying matrices together. This whole thing gives us a matrix, which then we multiply by the position. So the first thing is we're going to get the position in, and it goes from right to left order, how the operations happen. This position, we're going to multiply it by a world matrix, so that's going to be rotating the cube in 3D space. We're then going to multiply that by our view matrix, which is where our camera is sitting at, which then we finally multiply by our projection matrix to get us those nice points that we had before. Great. And I think that's actually the only change. Our fragment shader we're going to be able to leave the same for now. And finally, because we're interested in doing things in 3-dimensional space instead of 2-dimensional, I'm going to change vert position into a vec3. Great. So this is actually changing our vertex shader. Now let's change how we interact with that vertex shader in our actual program. So we're going to want to accessing these uniforms and set those values. So let's go down here. So first of all, I am going to change this because now we're introducing an x, y, and a z. For now, I'm just going to have the z component always be 0. Okay. Yep, so this is still going to be the same triangle with all of our z positions at 0. Our attributes aren't going to change the names anyways, but we are introducing one more element to the attribute, which means that the offset is going to be 1 greater. That now our color is going to be offset by 3 instead of just 2 like it was before. And that now also we have 6 points in every single one. Now this may or may not run right now. I'm actually not sure. Let's see what happens when we refresh the page over here. Alright, cool. So it doesn't show up, and the reason for that is I believe all those matrices default to having all zeros, and so it compresses everything into a single point, which you can't draw. I'm actually curious. There might be a pixel in the middle of the screen. Nope, there's not. Alright. So let's see. So now, for now, let's just set all 3 of those matrices to being the identity matrix, which doesn't actually perform any transformation. So after we have gone through and we've done everything with our attributes, let's come in here and let's get our uniform. So var mat world uniform location equals, and much like we did gl.get attrib location, we're going to do gl.get uniform location from our program. And I think I just called them mworld, mview, and mproj. Yes, okay. So var mat view uniform location get uniform location program mview. And then finally mproj. Proj just stands for projection. Great. So now that we have all of those, let's set those values. So for now, we're just going to say our projection matrix goes into a float 32 array of size 16. Let's go world view proj. So this sets them to having all zeros, and we're going to use that GL matrix library now to form all of those. So for now, we're just going to do the identity matrix just to make sure that we're connecting all of those uniforms together just fine. So the way to create an identity matrix is to say map4.identity, and then you give it which matrix you want to change on the inside. This is kind of more traditional graphics programming style. If you've ever done any DirectX or OpenGL programming in C++, you will usually have the output parameter, instead of being returned from the function, you have it as one of the parameters. Parameters to the function. Let's do that for the other two. View matrix. Identity. Great. So now we have 3 variables on the CPU side in our RAM that are just identity matrices that don't do any transformations. And we have the locations for those spaces in the graphics card GPU memory. Now we just need to send these matrices over to our shader. And the way you do that is through a function called the gl.uniform. And then from here, you can, depending on what type of uniform you're setting, it'll be a number and then a type. So for example, for 4 vectors, it'd be 4f or maybe 4u or something like that. For matrices, it's uniform matrix 4. That's how many, or that's how wide our matrix is it's 4 by 4. We are using floats, and I don't know what the v is, but there's a v there also. So uniform matrix 4fv. We give it which matrix we want to set. Map world uniform location. gl.false. Now if I remember correctly, I'm going to look this up really quick. Uniform matrix 4fv. I believe, as per the standard, this has to be gl.false, and the OpenGL call itself doesn't have to be false, but in order for it to work with WebGL, it does. I believe that has something to do... Yes, so this is the transpose, so it would be set to true if you want the matrix to be transposed, which works in the OpenGL standard, but apparently not in WebGL, according to Microsoft's documentation. Great, so gl.false, and then in here you give it the float32 array, and I'm going to mention that the type is important, float32 array of the actual data you want to set, which is world matrix. You'll notice that I created these as float32 arrays. With the GL matrix library, you could actually use just regular arrays, but then you would have to create a new float32 array anyways, so I figured just why not do it explicitly right there. Also, apparently it's faster, but I can't back that up on JSPerf. It actually didn't seem to back up that data. So let's set our other ones really quick. Uniform, I'll just do this, I'll just copy it. And I want to use the view matrix and the view transform. And then, whoops, gl.uniform matrix 4vf, map proj, gl.false, proj matrix. So now if we run all of that, we should get, whoops. Oh, okay, I did make a little mistake. Right, okay. So the reason it doesn't like that is we're setting the matrices right here, and we have the locations, and it's bound to this program, but we haven't told OpenGL that we're using that program. So I'm just gonna tell OpenGL that we are actually using that program right here. So tell OpenGL state machine which program should be active. Wonderful. Great, and so now we get the exact same thing we had before, except for with more code, more complexity, and more math. Awesome. Great, so let's start changing this to actually use the view world and projection matrices. So instead of using an identity, our world matrix is going to be a rotation eventually, but right now we're just going to leave it identity. Our view matrix, let's make a camera using the lookAt function. It'll go out to the view matrix. And this takes 3 parameters. Again, if we go back to our documentation over here, under mat4.lookAt, we need a 3-dimensional vector for the position of the viewer, position the viewer is looking at, and which way is up. So let's say that our viewer is at 0, x, 0, y, and then maybe like -5z. And then they're looking at the dead center of the world, just 0, 0, 0. And then up, let's say that 1 unit in the y direction is up, so y is up. And actually the way that it does the math internally to do all this, this doesn't have to be a unit vector. You could say something like that, and it would be just fine. But I'm going to use a unit vector anyways. So that'll give us a camera. And now that we have a camera, we do have to set the projection matrix, otherwise the view matrix is going to do something funky, and we're not going to be able to see our triangle anymore. So the projection matrix, we want mat4.perspective. That's going to go out to the projection matrix. And the perspective function takes in a field of view. So this is the vertical field of view in radians. Usually I've seen things like 45 degrees, but you can go higher than that. I'm just going to say 45 degrees. The aspect ratio, this is the viewport width divided by height. We're going to get that dynamically, but in an 800 by 600, that would just be 4 divided by 3, 1.333. And then the near plane and the far plane. And what these do is these say what is the absolute closest thing we can be looking at, and what is the absolute furthest away from the camera that we can be looking at and still have show up on the screen. The reason for this is when all this transformation is done, is you are going to have an x and a y and a z, even though your monitor only has an x and a y. There's going to be a z value between 0 and 1 that represents how far away from the camera it is. And that's going to be used for deciding which object should appear in front of other objects. So the closer these two numbers are together in terms of order of magnitude, the more accurate you're going to have, and the less you're going to have to worry about things accidentally appearing out of order. But it also means a narrower viewing field. So it's usually a good idea to have these within 5 or 6 orders of magnitude of each other, which is not even a problem. So let's see. .2 radian, 45 degrees in radians. We're going to say GL canvas.width over canvas.height. 0.1 is the closest, and 1000.0. Those are pretty standard numbers, so I'm going to use those. And now, if I do that, we may or may not be able to actually see anything. Mat is not defined. Oh, has to be mat 4, my bad. Cool. So now you can see it, and it's further away, and the reason for that is instead of drawing 0.5 in screen coordinate space, we're now drawing 0.5 in actual world space, and the camera is 5 units away, so that 0.5 is going to be much smaller looking. If we were to bring the camera closer, perhaps, so let's say instead of 5 units away, we only did 2 units away, maybe, it's a lot bigger, because now the camera is a lot closer. Great. So now to get the rotating effect, we're going to introduce the rendering loop, and this is what I intentionally did not do before, is every game is going to have a loop that updates as frequently as the computer is able to process it, and this loop is going to change the world in terms of what actually gets drawn. So in our example, it's just going to rotate the thing around. So let's see. So I'm going to make a function right here, and then I'm going to do a request animation frame on that function. And what this does is the request animation frame says whatever function is on the inside here, I want to call that function whenever the screen is ready to draw a new image. So usually once every 1/60th of a second. Another interesting thing to note about this is it will not call this function if that tab loses focus, which is really great if you're trying to save power like on a laptop or something. If the user switches a tab away, request animation frame will not be called, so it won't be drawing when no one's looking at it. So in here, I'm going to put the draw raise function, and then I'm also going to put a little bit of a rotation in there. So var theta angle, I'll call it angle, equals performance.now. This gets the number of milliseconds since your window started. So let's make that into number of seconds divided by 6. So seconds divided by 6, I guess, times 2 times math.pi. And so what this is this is going to be 2 pi, or 1 full rotation, every 6 seconds that it passes. It's going to accumulate it that quickly. And actually, you know what? I'm going to do this. Traditionally, it's not a good idea to create new variables inside of your loop, just because memory allocation takes a while. So let's see. So the var angle is going to be performance.now. And then I think I already have my world matrix up here, so I don't have to make a new one. I'm going to say mat4 dot rotate. Oh, I am going to want to do this. var identity matrix Okay, so that just gives us an identity matrix. The rotate function, the first parameter is the output, the second parameter is the original matrix, the third one is the angle, and the fourth one is the axis about which you want to be rotating. So I want to rotate the world matrix about the identity matrix by angle degrees and this axis. So I want to rotate it around the y-axis. I'm going to call that gl.uniform matrix for FE to update the world matrix. At world uniform location, gl false, world matrix. And then in here I'm going to do my draw command. So the first thing I'm going to do is I'm going to clear the screen back to the basic color. I'm going to erase everything from the previous frame. So gl.clear color 0.75, 0.85, 0.8, 1.0, gl.clear, gl.depth buffer bit, and gl.color buffer bit. And then once that's done, we can draw the arrays and request animation frame on the loop. If we do that, we should now have a spinning triangle. Great, so that looks really cool, right? But that's not quite what we came here for. We came here for something a little bit more elaborate, that rotating cube that I seem to have closed that window. So in order to do that, we're going to update our vertices, and we're going to have a new vertex for every point on that cube, every corner. So there's going to be 8 corners. And we're actually going to do more than that because we want the colors to be separated as well. So we're going to have 2 triangles for every face. There's 6 faces, so that's going to be 6 times 2 times 3, 6 times 12, that's a lot. And that's more than we need because a lot of these, the triangles for every face are going to share 2, I'm actually just going to pull it up. Cool, so there's 2 triangles in every single face. You can imagine like a diagonal line separating the 2 triangles, and they form a square. And because there's that diagonal line, and it's the 2 triangles, there are actually going to be 2 vertices that are going to be shared between the 2 triangles on that face. And so in order to save space, we're not going to re-specify a new vertex for every single time. So instead of having 6 points per face, you know, here, 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 and then there, 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 we're going to have just 4 for each of the corners. And we're going to use index arrays in order to accomplish that. Now, I have already prepared the list of points just because there is a jillion of them. So I'm going to copy and paste them over here. And you can see what we have is we just have, 4 points form the top, 4 points form the left, 4 points form the right, and you can see each one of them has a theme. So the top is always positive y, the left is always negative x, the right is always positive x, etc., etc. I'm going to rename this also to box vertices. And then I'm going to introduce a new list called box indices. And this is what is called an index list. And what we're doing right here is we're saying which sets of vertices form a triangle. So like for example right here, 0, 1, 2 says that the 0th, the first, and the second, these 3 vertices form our first triangle. Our second one is formed by 0, 2, 3. So it's formed by this one, and then this one, and this one. And just so on and so forth. And I'm going to let you look at that for just a second. You can pause the video here to copy all those values. I'm also going to put the source code on GitHub, so you can just copy them from there. And here are the indices. Let you see that for just a second. So we're going to have to introduce now an index buffer to complement our vertex buffer. And our vertex buffer is just going to hold the points, and our index buffer is going to hold the actual indexes, which is the order of triangles that we should be drawing. So var, I'm going to call this box vertex buffer object, box index buffer object. Now, an index buffer does not use an array buffer like a vertex buffer. It uses a different kind. It uses an element array buffer. But it does a very similar thing with a binding buffer and buffer data. I should probably change this to box vertices too. Great. So the position and color are still going to stay the same. All the vertex information, this is still going to stay the same. Going to stay the same. Going to stay the same. All of this is still going to stay the same. What we are going to change is, instead of calling a gl.drawArrays, we're going to use a different function called gl.drawElements, and this will use the index buffer instead. It still is using triangles. Now we have to tell it how many vertices to do. Luckily we have a box indices list .length, so we can just say draw however many are in there, draw that many triangles, or that many points I should say. It's not going to be that many triangles, it's that many points that it draws. The type of each one is going to be gl.unsigned short, which actually I led you astray. This is the type of the indices. We're using numbers and shorts. And then this is going to be 0. This is just saying we're going to start at the very beginning. If that was for, say, 3, it would say skip the first 3. This should not be a float32 array, so I already lied a little bit to you. Float32 is not the type that these are. These are going to be unsigned integers in 16 bits. So we're going to use uint16 array. Great. And let me just look over my notes. I'm pretty sure I'm remembering everything, and there's not anything extra that we have to do for that. Let's see if it runs. Okay, great. Yes, it looks like it's running, and it looks like the camera might be too close, so I'm going to move that camera back just a little bit. Yeah, -2, because the box, as you can see, is like, I don't know, has that large size. It's 2 by 2 by 2, so I'm going to move that instead of -2. Let's move it to -8. Great. Almost. So now you can see that it is drawing our rotating cube. But it looks a lot different than this, even though the colors and everything are still the same. The difference is that this one is drawing a true cube, and this one is drawing things that it should not be. You can see if you watch this green side, even when the green side passes behind, it's still being drawn, which is not okay. So we are missing something. The first thing that we might be missing is the depth test, which I'm not sure if we're ever actually enabling that. I don't think we are. Up here at the beginning. Yeah, we are not. So we do need to enable a couple of things, and I'm going to make sure that I have I don't think I have a reference to that. Just a second. I'm not entirely sure what the syntax is here, so I'm going to just really quick make GL something global so that I can look at it. gl.enable gl.depth test. Okay, yeah, so that is what we were missing, just making sure. Boop, 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 boop. So the way that it's working right now with all that is it's not caring about the depth, it's just kind of drawing whatever it happens to come across first. So in this case, the green is being drawn after the red no matter what. So you can see that the green cuts off the red, but then it is not cut off by the red. And the reason for that is the depth test. There is something that the rasterizer can do. It can look at the pixels that are already drawn on the fragments, on the frame buffer, and it will say, if we have drawn something already at that pixel, only draw that pixel if it's closer to the virtual camera that we've set up. And we enable that by just saying gl.enable gl.depth test. Great. So now if we reload it, it should be just fine. Now there's another thing that I'm even going to mention before that, because this presents with us another problem. even if we do enable the depth test, the rasterizer is still going through all of those points, and it's still forming for every single pixel on this green square. It's doing a bunch of math, so it's wasting work even when it's behind the red box. And there's a way that we can prevent that, and it is called backface culling. So for our GL, I'm going to show you how to do that again the same way. Oh, how was this done? Let me look at my notes. I'm not sure I actually enabled it in my notes, so that's why I'm... Okay, I did. So the calls are a gl.enable, and this will enable certain features. gl.cull face is what we want, and that's really it. You could, for good measure, also tell it which side you want to cull, and cull means just get rid of. And in this case, we want to get rid of the back of all of the faces, but we could also say front, which would be kind of funny. It would give us the exact opposite effect that we would want. So, cool, I guess. So cull face back, and then we also tell it which side is the front face, with either .cw or ccw. And this just says that a face is formed by the order of the vertices appearing counterclockwise to each other. So let's go and actually add that to our code. So I'm going to do that back up here where we initialize OpenGL. I want to enable the depth test. I want to enable backface culling. And I think, okay, good. That is the only place I had it. Great. So now we have all that, and the rotating cube appears as we should, and take my word for it, it's not doing extra math for the faces that go out of view and go behind the cube, that are facing the wrong way to the camera. Let's see. And I do believe that is almost everything, but as you can see, just as a final note, in this demo I had 2 different rotations going, and in this one I have just one. It's rotating around a single point. This one is both rotating forward and rotating laterally, so around the x and the y axes. The way you would achieve something like that is you would form 2 rotation matrices and then multiply them together. So let's do this, like var x rotation matrix and then down here I'm going to form the rotation matrices. So this one's rotating around y. I guess it's going to be x and y, huh? Y rotation matrix, mat4.rotate. This one is going to be our x rotation matrix. And I'm going to take that angle and divide it by 4 so it goes slower. Great. Cool. And then I'm going to multiply those 2 matrices together to form our world transformation matrix. Alright, and what this does is this just says multiply x rotation matrix by y rotation matrix and spit it out into our world matrix. So now if we do that, you can see it's rotating around 2 different axes, so we can see all of the sides. And the rotation for this one is a little bit different. I could change the order of those transformations here to give us a different effect. So maybe I want to do the y rotation and then the x rotation. And so we would get, yep, there's the one more like the video I was showing you before. And I think that's really it. So that's how you do 3D stuff in OpenGL, which I know is the thing that you were probably thinking of when you started OpenGL tutorials. That's how all the math is done, at least conceptually, and how we can present a full, more complicated object spinning around. Now, in the next tutorial, I'm going to be covering doing... oh, what should I do in the next tutorial? You know what, in the next tutorial I think I'll cover texturing, so I think I'll cover adding pictures to this. So instead of making this just a colored box, maybe we make it a crate. I'm also planning on doing ones on lighting, loading from a file, organizing space into a game. We'll see. Let me know in the comments what you would like to see, and I'll probably do a tutorial on that. Again, thank you for watching. Hope you enjoyed. I will be posting the code for this on GitHub and that link in the description. Thanks.